Hello, welcome again to the lecture series on Control Systems Engineering. Let us continue our discussion on error analysis. Let us work out some more examples here and also find dynamic steady state and dynamic error for defined problems. Here, a second order servo is characterized by the differential equation d square c of t by dt square plus 6 dc of t by dt 16 c of t equal to 16 r of t. It is supplied with a ramp input of 2.5 centimeter per second. Determine transfer function, time response, and steady state error. So we will take this differential equation. If I take the Laplace assuming all initial conditions to be 0, this will become s square c of s plus 6s c of s plus 16 c of s is equal to 16 r of s. So c of s by r of s is 16 divided by s square plus 6s plus 16. You got the transfer function. Now you have to find the time response for a ramp input. Ramp input is a by s square. A value is 2.5. So 2.5 by s square is r of s. So c of s is 16 r of s, s square 6s plus 16. R of s is 2.5 by s square. Then you will get this. Let us split this into partial fractions. A by s plus b by s square plus cs plus d divided by s square plus 6s plus 16 because it's a quadratic equation. Then let us take LCM. Then let us compare coefficients. Coefficients of s cube, a here, c here equal to 0. Similarly, coefficient of s square here, here, and d. We'll get this equation. Then coefficients of s, we'll get 16a plus 16a plus 6b is equal to 0 you get. Constants when I do, I'll get 16b is equal to 40. So from here I'll get b, then back substituting we'll get all these values. Now let us substitute into this. This is not in standard form. So first of all this should be converted to s plus a whole square plus b squared. So s square plus 2as plus a squared plus b squared. So what we have done is s square plus 6s. So 2a is equal to 6 means a equal to 3. 3 square is 9. Out of 16, 9 if I take 7. Then I can write s plus a whole square plus b squared. So then I have to reorganize this. Okay. Then again I have to split this one. S plus a divided by s plus a whole square plus b squared. 1 by s plus a whole squared plus b squared. Now if I take Laplace inverse, I'll get a response. Okay. Right. So steady state error is limit s tending to 0, s r of s 1 plus g of s. R of s is 2.5 by s square given. So c of s is 16 divided by s square plus 6s plus 16 is equal to g of s plus by 1 plus g of s. From that I have found out g of s. Then I have substituted into that equation s g of s divided by 1 plus g of s, right? S r of s divided by 1 plus g of s. I have substituted and I have got the answer. So steady state error is this. Next problem. A servo mechanism is used to control the angular position theta naught of a mass through a command signal theta I. It is something like this. Theta I, theta naught, and this is J. Okay, the moment of inertia of the moving parts referred to load is 2000 kg meter square. That is J value. The motor torque at the load is 6.88 into 10 to the power of 4 Newton meter per radian of error. Torque applied. That is also given. The damping torque is also given. This is damping torque. Say C of T or F of T. Ft. Find the time response of the servo mechanism for a step input of 1 radian. Determine the steady state error when the command signal is a constant angular velocity of 1 revolution per minute. So theta naught of S by T of S we can derive. We'll get this one, this transfer function. Error is theta I of S minus theta naught of S. And he has given T of S by E of S equal to 6.88 into 10 to the power of 4. So T of S I got. Okay. Theta naught of S, T of S is this value. I substitute. This equal to 1 by J square plus Fs. So theta naught of S by theta I of S is given. Now we can get this G of S divided by 1 plus G of S H of S like. Okay. Fine. We have got theta naught of S by theta I of S. R of S is A by S, 1 by S. So 1 by S is substituted here. Then split this into partial fractions. You can make the arrangement for this. Find ABC by comparing coefficients. Then substitute here. Okay. I have done the similar kind of problem. That's the reason why I'm not getting into the details. Then I'll get the, if I take inverse Laplace, I'll get this solution. Okay. R of S is 1 revolution per minute, 2 pi radians per 60. So you will get this one. Steady state error is limit S tending to 0 divided by S R of S divided by 1 plus G of S. From here I am getting G of S. S R of S 1 plus G of S. Okay. Now substituting S is equal to 0, you will get a steady state here. Okay, only you have to carefully do this, otherwise it's a substitution problem. A feedback system employing output rate damping is shown in figure. Okay. In the absence of derivative feedback, that is K not equal to 0, determine the damping ratio and natural frequency of the system and what is the steady state error resulting from unit ramp input, assuming this equal to 0. Okay, we will do that first. So then your feedback, your block diagram looks like this. You get G of S, then okay, so then C of S by R of S, then you compare with the standard form from which you can obtain omega n. Also you can obtain zeta value. Okay, this is the first part of the problem. Then steady state error is limit s tending to 0 s r of s divided by 1 plus g of s. Okay, for unit ramp input it is 1 by s square. I have substituted and I have got the steady state error value. Let us go to the second part of the problem. Determine the derivative feedback constant K naught, which will increase the damping factor of the system to 0.6. What is the steady state for unit ramp input with setting of derivative feedback constant? So now if I simplify all these things, I'll get C of S by R of S is equal to this. Now you observe here, coefficient of S is 2 plus K naught. So we get omega n square is 3.16 radians per second. And 2 zeta omega n is 2 plus K naught. Zeta he has given, omega n is available. From that you can find K naught. So now our steady state error formula is this. R of S is 1 by S square. G of S is this. Then I'll get steady state error value. Third part of the problem. Illustrate how the steady state error of the system with derivative feedback to unit ramp input can reduce to the same value as in one above while the damping factor is maintained at 0.6. Zeta is 0.6. Now omega n square is equal to k, so omega n is equal to root k. Okay, so G of S is this. So you got C of S by R of S. 2 zeta omega n is 2 plus k naught, omega n square is k. Correct. So it is 1.2 root k is equal to 2 plus k naught. Error steady state is 2 plus k naught divided by k, that is 0.2. From that 2 plus k naught is equal to 0.24. Okay. So now 1.2 root k must be equal to 0.2 k. So now solving this, we will get k equal to 36. That k value if I substitute, I will get k naught value. That's how we can solve this example. Figure shows a system employing a proportional plus error rate control. Proportional is this, error rate controller is this. Determine the value of error rate factor K so that the damping ratio is 0.5. Determine the value of settling the maximum overshoot. Determine the value of maximum overshoot. Find the error steady state for unit ramp input with and without error rate control. Comment upon the effect of error rate control. First of all, when KE is equal to 0, this will become G of S, S plus 1. So from that we can find C of S by R of S. You can compare with this and you can find omega n value as well as zeta value. So now error steady state for unit ramp input we can find 0.2. Now let us consider KE now. Now G of S will change. Accordingly find C of S by R of S. Again omega n is 3.16, but 2 zeta omega n is 10 plus KE, so zeta is given, so KE can be found out, 0.116. Now again you find error steady state error here. So both the cases we have got the steady state error same. There is no effect of Ke on steady state error. Settling time or overshoot. Settling time of maximum overshoot. I think this is not correct. 3t is this settling time. We can easily find out. There is no problem at all. If they mean peak time, you can find out pi by omega t. It's not a problem. And omega d is nothing but omega n under root 1 minus zeta square, and we can find out peak time. A thermometer requires 1 minute to indicate 98% of the response to a step input. Assuming thermometer to be a first order system, find the time constant. If the thermometer is placed in a path of temperature of which is changing linearly at a rate of 10 degrees per minute, how much error does the thermometer show? First order system, 98%. From that 1 minute t you will get. So t equal to 0.253 minute time constant we can find out. Now it is subjected to ramp input because it is 10 degrees per minute. So now split this into partial fractions. Find out the ABC values and substitute over here. Find C of t. Error is R of t minus C of t. Error is 10t. This is the thing. So now we can find out what is the error value. So the output of a control system is given by C of t is given here. Determine the transfer function of the system. It is subjected to unit step input. Also find the natural frequency, the damping ratio of the system. Output is given. If I take Laplace, this is 1 by s, and you will get 1 by s plus a. So 0.2 1 by s plus a. 1 by s plus a. So you'll get 1.2 s plus 10. So now C of s is equal to, take out 1 by s common. C of s by 1 by s I have taken because it is ramp input, step input. So I can replace that as R of s. So then I will get this way. Okay, now C of s, G of s 1 plus. Now if you take LCM, you will get this. So that is the one you will get. So then you can compare and we can find out omega n value as well as zeta value. Okay, that's fine. So carefully analyze the problems and do it and solve. Now let us talk about dynamic error. So you know this is our error transfer function. This one let us represent by a series. 1 by k1 plus 1 by k2 s plus 1 by k3 s square. I am approximating this by a series. So then E of s multiplying with R of s, I'll get this one. If I take inverse, if I write it reverse, it should be R of t. This should be R dot of t. This should be R double dot of t. Here you can call K1 as dynamic positional error coefficient. Okay, 1 by K1 is limit s tending to 0 W E of s. Similarly, one by dynamic, this is differentiation because it's velocity. Third one, second differentiation, it is velocity. Okay, so we can find out 1 by k1, k2, k3 using this. Now you see it, the transfer function is given. Open the transfer function is given. We have to input is given. So we have to find that. Right. Find k1, k2, k3. So g of s is given, r of t is given. W e of s is defined like this. 1 by 1 plus g of s h of s. Correct? So that is nothing but this one. So put the W e of s here and get k1. Again you have to differentiate this one to get k2. After differentiating, substituting s is equal to 0, you will get k2. K3 is defined like this, half limit s tending to 0 d square w of s. So that one, once again, you need to differentiate, substitute s is equal to 0, you will get this. So you got the k3 value also. So now E of t is 1 by k1 r of t, 1 by k2 r dot of t, 1 by k3 r double dot of t. Substitute here. Then you will get this one. That is the error. Sorry. You have forgotten to define W E of S. So W E of S is this, is given here. Yes. That is 1 by 1 plus G of S H of S. Yes. Let us solve another example. C of s by R of s is equal to 3s plus 10 divided by 5s square plus 2s plus 10. Determine the dynamic error coefficients k1, k2, k3. So C of s by R of s, from that we'll get G of s. Then W E of s is nothing but 1 by 1 plus G of s. Get this. Then I have got my W E of s. So I can find 1 by k1 is limit s tending to 0. So k1 is equal to infinity. 1 by k2 is limit s tending to 0. dw of s. Only thing is carefully differentiate this a by b formula. Okay. Then you will get k2. Again k3 is of limit s tending to 0 d square we of s. Once again differentiate that and substitute s is equal to 0, you will get k3. Okay. So the difference between the dynamic error and static error is there. Error transfer function is s r of s divided by 1 plus g of s h of s we define. Here we have w e of s, which is e of s by r of s as 1 by 1 plus g of s h of s. That's how it is defined. Okay, that way we can find the dynamic error now. So now you have understood how to find steady state error and Kp, Kv, Ka, that is position error constant, velocity error constant and acceleration error constant. Similarly, how we can calculate the dynamic error coefficients K1, K2 and K3. I think This is how we can calculate the error values. Thank you very much.